Hey, Mr. Gustin, back in the physics classroom. Are you struggling with the inclined plane activity? It's not easy. Definitely some challenges here. Let's talk about this constant velocity thing. So you go ahead. You already have your mass, or your object rather, on the inclined plane. You elevate the inclined plane to an angle of theta so that it moves at a constant velocity downward. But now what? How do I find the amount of friction that exists there? And I'm not so much concerned about the amount of friction specifically because I know it's going at a constant velocity. What I'm more concerned about is the coefficient of friction. So that way when I raise that ramp up to 30 degrees and launch it off the table, I can calculate how much friction there is. So I need to find mu k. I really need to know what the coefficient of friction, kinetic friction, is for this. Well, let's go ahead and start doing some things that we would normally do. Let's go ahead and write out an F net expression parallel to the ramp and perpendicular to the ramp to just see what we have here. I'm not sure what's going to happen, but I always do this just to organize thoughts. So let's go with F net perpendicular. We know in the perpendicular direction there's no acceleration, so F net perpendicular 0 newtons would be F normal minus Fg perpendicular. I've got that one here. I'm also going to come down here and say F net parallel to the ramp is equal to 0, constant velocity, and therefore Fg down the ramp, or parallel, minus force of friction, kinetic. These are the two things that I have here to work with. Okay, so I know that Fg parallel is equal to the force of friction, kinetic, constant velocity, and that the normal force up here, Fn, is equal to Fg perpendicular. Well, I see a substitution kind of happening, right? Like, if I don't know force of friction, I can always plug something in to find it. And here's what it is, right? Like, I need to find mu. Which of these forces is mu secretly hiding behind? Like, mu is coefficient of friction. Mu is hiding behind force of friction. Let's go ahead and rewrite this. Fg parallel is actually equal to mu k times the normal force. That's where it was hiding, right? I just expanded it. I substituted it in. How do I know that? I know that because of the fun equation. Force of friction equals mu times Fn. Okay. Do I know the normal force? I don't, but I do know this. I know that the normal force is equal to Fg perpendicular. Perpendicular force is going to be that force right there, cosine. Fn is going to be equal to Fg cosine theta. Okay, let's keep substituting. Mu k times the normal force is now Fg cosine theta, Fg parallel. Do I know Fg parallel? Not really. Let's substitute. Fg parallel is that component. It's sine. I'm going to bring it up here so we can keep seeing it. So Fg parallel is the sine. So Fg sine theta is going to be equal to mu k times Fg cosine theta. I think I'm done substituting things in. Do I know what the force of gravity is acting on my object? I mean, it's different for all of us, right? I had Tic Tacs. You may have had a book or an iPhone or a calculator or who knows what. So our forces of gravity are different. I don't have a scale at home. Do you have a scale at home to measure the mass of something? I don't think I need it. Folks, there's something here. Both of these terms have Fg in it. I can cross out Fg. I can divide both sides by Fg. Here's what I'm left with. I'm with the sine of theta equals the coefficient of kinetic friction times cosine theta. Folks, the coefficient of kinetic friction is simply, in this case, very specific to this case, the coefficient of kinetic friction is equal to sine of your angle divided by the cosine of your angle. That is very specific to this case. How did we get there? We started with our F nets. We substituted some things in, right? We did a little physicsing, but eventually we saw that the mass of this object didn't matter. The only thing that mattered in terms of how sticky the two surfaces are is the angle. That's your coefficient of friction. Now, you should be able to raise your ramp up to 30 degrees, raise the ramp about a meter off the ground. So find an object that can lift your ramp about a meter off the ground and then raise it to 30 degrees. Send that thing down the ramp and predict where it's going to land using some forces and kinematic equations. Hopefully this was a helpful hint for you. Now, go finish the job yourself. See ya!